So if I'm looking for the best match of, this image, it is of course the image itself. But now we want to synthesize something, which is 20 times the size, let's say, or 100 times the size. We want this, 10 times 10 as big as these patches that I'm showing here. We're looking for a generating algorithm that will create good looking images or textures from a very small sample. So let's say you want to, print let's say you want to print a tapestry, but you are, it should be larger than this one. But if you just replicate it, you will see the replicating structure. You want it to look the same. You want a generative model that will create you textures. Any other ideas? So I myself would be hard pressed, or I'm spoiled because I've read the literature already. So now I think, yeah, that makes sense. But I wouldn't have thought of it myself. So let me give you a little bit of history. Much of the research into texture synthesis analysis was pioneered by a guy named Jules, and so he in the 60s, I believe, he claimed that matching moments, and then he had a theory about which moments it had to be. Is enough to produce perceptually similar textures. So by moments, I mean something like the variance in regions or correlations between pixels and such. And now, a few decades later, one tends to think that this can be true only for, let me put in quotation marks, very stochastic textures. So if you have, something like the carpet here, which is sort of random, dirty grayish, it would work pretty well for that, but it wouldn't work for the apple example. A very influential paper was a paper called Frames by Zhu, Wu, and Mumford in International Journal of Computer Vision, 1998. And these are all excellent people. Mumford is also known outside image analysis because he's a Fields Medal winner, and the others have also gone on to great careers. They published a forerunner of a method that is important nowadays, a method which is called field of experts. They look at the following problem. They start, I'm showing an excerpt from their paper here. They start by taking this sample texture A and then generating a random field that looks like B. Now they have a large array of possible filters, and we will talk about filters much for the next 2 weeks, but not today. So these filters take shift invariant linear combinations of the pixels. So we can have smoothing filters, derivative filters, and such. And they propose to look at the filter responses from the original training patch A, to look at the filter responses from the current synthesis B, and to compare the histograms of these filter responses. Now, among this set of predefined filters, there will be one for which the responses are more different than for any other set of filters. So there's one filter that will be most discriminative. that can best tell apart the differences, that can best distinguish between the original training patch and the currently synthesized patch. They then include this filter in their method in what may be called a filter pursuit strategy, and try and synthesize a new image which, according to that filter, has the same output response histogram as the training image. And that gives you the result in C. And now they look again for the most discriminative filter and again sample a new image that should also match the filter responses in terms of histogram of that new filter. That gives you D, and then E and F. That sounds very nice, and it is. However, it is really, really hard to sample an image such that the histogram of a specific filter will have a certain form. So you need to do something like Markov chain Monte Carlo sampling, and that can take you a long time. It's one problem. And then beyond taking a long time, it works, I would say, very well for the kind of text shown here. So A and F, you could argue that training worked all right. But I want to show you some textures for which it has bigger problems. So it works, quite okay with something like this, cheetah and a blob texture. But now look at these. So these are synthetic textures. This is perfectly admissible. But if you try and use the kind of approach taken here, the best you can come up with is this. You could say it's astounding that you can learn that at all in such a way. But it's not really a satisfactory replica or generalization of the training texture that you've seen. And after all this build-up, I want to show you an algorithm which is super simple and does great on all kinds of examples. It's my favorite texture synthesis algorithm all around. And it works for both, the very stochastic ones and also structured ones. So here we go. This is, the paper is called Image Quilting for Texture Synthesis and Transfer by Efros and Freeman, published in 2001. And here you see a couple of examples of, on the left-hand side, the training textures, and on the right-hand side, what they can produce. In particular, you see that this also, so this was the kind of texture that this frame approach had a hard time with. And you can see that it generalizes perfectly. I also find it astounding that you can feed text into this, and it will produce you realistically looking garbage text. And it's really, well, I'm still puzzled, even today, after having looked at this many times, how good those results are. Okay, here's how they do it. They take the input texture and chop it up into blocks. Now, if you simply put these blocks one next to the other, you would get, these artifacts here, where you can clearly see where how you concatenated these blocks into an image. It works a little better if you start with block number 1, which is actually a bit larger than you see here. So maybe I should use a different color here. Block number 1 is actually a bit larger than the part that you see. So the part that you see is here, but the block is actually a little bit larger. And now for the neighboring block, amongst all possible patches from the input texture, you can choose one that is a pretty good match according to the overlap here. And in this way, you can, in lexicographic order, build from left to right. And then you can start with the second row where you want to have good match in the overlap area between both your leftmost neighbor and your uppermost neighbor, and so on. And it produces something which, you know, looks already not so bad, but you can still discern the boundaries of where these blocks meet. And here's their proposal. You do what I've just described, but this time, so here the blocks were selected according to a good match in this overlap region, but then the pixels left of this line were taken from the left block, and the pixels right of this line that I'm drawing were taken from the right block. What they propose in this paper is to find the best possible cut within this overlap region. So they look for a single line from top to bottom and take the pixels from B1 on the left and the pixels from B2 on the right, and obtain something very nice looking on the right hand side. That's a strategy used to produce all of these pictures here. So let me give you the algorithm. The image quilting algorithm. So in the words of their paper, you go this is quoting literally from their paper, go through the image to be synthesized, in steps of one block, where the step size is a little bit shorter than the block length to allow you to give you some overlap. So this is the outer loop. And then within this loop, do the following. For every location that you visit, identify matching blocks from the training picture, by matching, I mean that you compute the error that this overlap here produces, and if this error is lower than some threshold, you keep it as a candidate. And from all these candidates, you randomly pick one. Here is a minor, smart technical detail. They don't use a fixed threshold, but they consider a large number of blocks from the training image and record the best matching error from any of these blocks, and then accept as candidates everything up to, I forget, everything that has an error that is up to 20% larger or so. So these are the candidates that they keep, from which they pick just one, and they then compute what they call the error surface between the newly chosen and the old blocks. Where this error is dead simple. They literally just take the sum of the squared errors of the color values in these pixels. So let's say that this is a part that we finished already, and now here is the new block. Then the error surface is computed here, and the error surface is computed there. And then the cheapest path is sought, the cheapest vertical path through the red area and the cheapest horizontal path through the green area. So compute this error surface, find the minimum path along the surface, which then becomes the boundary of this new block. And then this block is added, and then this thing is repeated until we have completed, until we have synthesized a whole image. There are almost no parameters, so you need to choose, of course, this error function, but I've told you they've used the simple one you can think of. You have to choose also the overlap. They used 1/6 of the block size in all their experiments. Okay, now about this minimum path, who knows how to compute a minimum energy path in a surface? Who has followed the algorithms and data structure lecture? Wow, okay, so we'll do that. So let's say that this is an area in which I want to find the cheapest vertical path. And let's say this is what I'm showing here with this grid. This is the overlap region between the two blocks. And we have, as an entry in each pixel, the matching error. So I'm making up some numbers. So maybe here the matching error is 28, and there it's 43, and there it's 35 and 67, and so we have numbers everywhere. And we want to somehow find the cheapest path. Now the way this can be done is by means of dynamic programming. So I have start here, and because I'm looking for a vertical path, I have an end there, and I'm connecting start to each of my pixels in the top row. And I'm connecting end to each of the pixels in the bottom row. I'm now looking for the cheapest path, and this cheapest path has the following property. Let's say, for the sake of argument, that cheapest path is this. It has the property that if this is the globally cheapest path that exists anywhere, where I only admit for my path 3 possible steps, so at each position I am allowing my path to either, oh, and I made an error here. Bless you. So let's say at this point here, I'm allowing my path one of 3 choices. It could either continue here, or it could continue there, or it could continue here. And to use a dynamic programming algorithm, you need the property that the solutions are nested, that the complete solution to the problem will also comprise the partial solutions. So the partial solutions must be a true subset of the complete solution. So in other words, I'm using the argument that if the red path is the globally optimal path, then if I'm only looking for a path up to, let's say, up to this line here, then the cheapest path that leads only up to this row must be a subset of the path that goes all the way down. Not true. I need to restrict myself to this pixel here. So what I want to say is that the cheapest path that leads to this pixel, so if this pixel lies on my total or on my global solution, then the path leading to this pixel must also be part of the global solution. Because if there was some other path, if there was some other path that led here and that was any cheaper, like this one here, then that path should have been part of the global solution. So this is the property that we need for dynamic programming. Okay. Now to find this global path, we use this property that I've just mentioned, and we have we can compute the total cost that I incurred in getting up to this pixel here. And now I have a couple of options. I could either go here or there or there. And I can compute these new costs, I can compute these new costs as sum of the costs for the path up to the previous pixel plus the cost that I incur in going to these new latest pixels. And out of these, I will take the minimum, which in this particular example here happened to be this pixel here. So I am always trying to find the minimum of my previous cumulative cost plus the transition cost and I am minimizing this over all allowed successors. And I'm doing this iteratively here from the very start. And this allows me to put in a number into each of these pixels here. So in each pixel, I always have the smallest cumulative cost of reaching that pixel. And I can do this row by row for my entire problem. At the end of which I have the smallest cumulative cost of reaching any pixel. So let me put that in words. I have a forward pass which finds the lowest cumulative cost of reaching any pixel. In our example here, starting from the top. And then secondly, I have a backtracking or backtracing step where I find the explicit minimum energy path by following a steepest descent which commences at the end node of my graph. And here these edges connecting the pixels to the end node, those are zero cost edges. So they incur no transition cost. These also here are zero cost edges. Okay, so this is a really important algorithm, and that's why it would be good if you could ask some questions here, in case I've not made myself totally clear, which is quite possible. Go ahead. This is exactly the reason why I corrected myself. So let's say there is a really cheap path, let's say, going down here. At which point, the costs here are, infinite, and it's not going to be, it cannot go through there. It does not matter because we compute for each point the smallest cost of getting there, starting from the top. In particular, if I only allow, the kind of transition that I showed, like from here to here and from there to there and to there, you can infer that the cheapest cost of getting here will also be infinity, and so on. And that means if at the end my lowest cost of getting there is some finite number smaller than infinity, if I now do a steepest descent backward, I will follow the red path rather than the green one. So yes, this search finds all the cheapest paths, including the ones that are cheapest up to a given row, but lead no further or only at a very high cost. So this is why I corrected myself earlier on. I had started drawing this line, and I had said the cheapest path leading up to this line must also be part of the global solution, and that is not true, because if I draw the line up here, the cheapest path leading up to this line is the green one, but the cheapest path leading to the very end is the red one. So the condition that I have is that the cheapest path, well, let's say the red one is the cheapest path overall, the global solution, then the cheapest solution leading to every pixel on that red path, on that global solution, must also be part of the global solution. Maybe too much global in a sense, but is it? Okay, let's take some more time for questions. This is really deep and important algorithm, one that you will see again and again. So is the algorithm really cheaper as compared to trying out all paths? So the set of all possible paths is very, very, very big, because if I So the argument is a little bit simpler if I use toroidal boundary conditions, where I can, walk out the left side and enter again on the right side of my problem. Then the total number of paths is that from every of the first pixels, I can go to any 3 of the subsequent pixels, and then from any of those, I can go to any 3 of the subsequent pixels, and so on. So I don't know, something to the power of. This is very many. Whereas here, our effort is just number of pixels times 3, essentially. Because for each new pixel for which I want to compute the cumulative cost, I just check what is the cheapest way of getting there. This picture is starting to be a bit full of scribbles. So, let's say I have already found a cost for this previous row here. And I'm doing this in lexicographic order. Now I want to know what is the cost, the cheapest cumulative cost of getting here. Now the only legal ways to get here are from this one, or from that one, or from that one. So I'm using this cost here plus, the transition cost, which would be the error that I have at the current pixel. And this is what I meant here. I minimized this thing. So it's just the number of pixels times 3 as opposed to some exponential number of paths that are possible in general. So it's a super cheap algorithm, and it gives you the globally optimum solution, which is why it's a very beautiful and important algorithm. So questions about A star in beam search, you just, rather than following up on all possibilities, you have like a cache of the best few solutions found so far, and then keep going with only these. You can trick such algorithms by letting, let's say you have a cache size of k, and you can build surfaces where all the k paths that are cheapest up to a certain row then end up in such infinite well potentials. But in practice, that is a very good algorithm, of course, and it's applicable in more difficult scenarios than this one, where I severely restrict where I'm coming from, where I'm going to, and what are the allowed transitions in between. Do you have more comments or questions? Yeah, so here it's just RGB value in the one patch minus RGB value in the another patch, which is a 3-dimensional vector, and then you take the squared Euclidean norm of that 3-dimensional vector. Very simple. The question is about taking into account what's on the left and right of the visual path. The thing is that natural images have some degree of smoothness, and it is in principle possible to construct mean images that have a perfect seam but look totally different on the right and left hand side of this path. And yes, you could trick the algorithm with that kind of mean, error surface. But if you now take, an image like, well, the ones to be synthesized here, because they have some smoothness, when you find, so remember that everywhere here we have these, using a different color again, everywhere here we have these cut paths that were found. They were found patch by patch, horizontally and vertically. And yet, because the blocks on either side of such a cut have some smoothness, it looks like you get a good match between the blocks overall. And these cuts are found So because the image is created block after block in lexicographic order, these cuts are found in always one horizontal and one vertical cut at a time, and then the next block is added. Absolutely. So does it? Yeah, exactly the same. Look, this. If you look at these apples that look towards the observer here, or let me take a different pen. This one, this one, this one, this one. If you look in the original training image, there's just a single source. So all of these. Oh, no, it. Let's see. Bigger parts that are identical. Yes, it could. For depending on the input image that you have, it could happen that the if I take let's say if I take a binary image, which just has black and white, then you could also generate larger objects that somehow so I think the Apple example shows it nicely. On the one hand, you have repetitivity, and on the other hand, not, because we only use blocks, that are maybe this size from the training image. Okay, I have a couple more examples. Maybe this also answers the question. So I find it quite admirable, I have to say. And then in the original paper, there are also fun examples where you have a real natural photograph, and you append to it on the edges stuff that looks like a natural extension. Well, this is probably even this part here is already playful, and the other part that I've just mentioned is even more playful. But the reason why I'm showing all of this is because this is an example of an algorithm where you let the data speak. So let me take this as morale of this part of the lecture. What do I mean by that? This is a non-parametric approach. So rather than training a Markov random field that will produce an output with the correct statistics, you simply take the training exemplar or fractions of the training exemplar. And taking a few steps back, this is a revolution that one has also seen in machine learning, and that is, on the one hand, thanks to the availability of very large training sets, and on the other hand, the availability of fast computers to, essentially use the exemplars. And having a big enough training set means that you are not so susceptible to overfitting as one would normally expect. So this is a nice algorithm, which I think it's still state of the art today, because anyway, for texture synthesis, again, there is not a number. You cannot say in a number or measure in a number that this algorithm is better than that. You have to ask a human which looks more natural. And I think it's still state of the art today, and it's conceptually extremely simple. So if you spend an afternoon, you can implement this algorithm, whereas this training of higher order Markov random fields and such, which is mathematically intriguing and elegant and everything, this is a major project if you were to implement this yourselves. Okay, and in general, I want to be agnostic about such things, so we we use, what gives you the best results at the lowest effort. And in this case, it's such a simple algorithm. Just as a postscriptum, this seam selection, so finding the optimum cut between two adjacent blocks, can also be used to do other things. And I'm showing a SIGGRAPH 2004 paper here. You have as input 4 photographs of a family, and there are some images. Let's say in this image the guy was looking the wrong way, but in that image this person was looking the wrong way, and there is not a single perfect image. So you want to stitch it together from, in this case they were using a total of 5 images. And what this algorithm allows you is to put a scribble on the images telling what part you want to keep. So you see there's a blue scribble here, which says I want to keep this part of the left image. And then there's a yellow scribble. So the lady with baby I like best in the yellow image. And well, these two people had the nicest smile in the red image, and so on. And now I want to put this all into one. So as an energy optimization problem, it means it's a multi-label problem. You have at each pixel 5 possible labels, namely which image you take the content from. We have some constraints, namely at these pixels where my scribble is, I definitely want to use the blue pixels, and here I definitely want to use the pixels from the yellow image, and here I definitely want to use the pixels from the red image, etc. And then we have a smoothness constraint, meaning if I used the blue image for this pixel, then I also want to use the blue image for the adjacent pixel. So we penalize label changes. You can optimize that using a Markov random field, and it gives you, nice results where everyone is looking in the camera and happy and smiling and all. How to do the math of this? So how to optimize such a multi-label Markov random field, we will also talk about at the end of the semester. Here I just wanted to give it as another example where this seam selection can also be used. Any more questions? Those were convolution filters. Essentially, it does not matter because, so what kind of filters were used is the question. The authors prove in this paper, just as a side result, that if you project a high dimensional distribution onto all its possible margins. So let's say if you know all projections of a high dimensional distribution on one-dimensional lines that lie in this space, if you know all projections onto all lines that are oriented in any fashion, that you can then reproduce from that information the shape of the full high dimensional distribution. And in that sense, all that you need are many different directions or many different filters. And well, I think they didn't use random filters. I think they used smoothing, derivative, and such, but I don't know for sure. I would have to look it up also.